Hi, I'm John May from USC ISI, and I'd like to tell you about style transfer with multi-iteration preference optimization by Shuai Liu and me. This work is about textual style transfer. What that means is that we want to change an input text from, say, the orange style into the green or blue style while preserving the meaning of the input. We might want to do this because the original style of the text is inappropriate for its domain of use, or to protect the identity of the text's author from adversarial authorship detection systems. In this work, we're going to follow a two-phase framework. Starting from a pre-trained model, we're going to acquire some parallel or pseudo-parallel data that exhibits the phenomena we'd like to learn, and we're going to do supervised fine-tuning where we maximize a language model objective on that data. After that, we're going to use preference optimization techniques like PPO or DPO to align the behavior of our model with some desired reward metrics. This is fairly common. It's the standard approach behind ChatGPT and InstructGPT, and it reminded us of the way we used to do machine translation optimization before the neural era. Back in those days, we also had a metric that we wanted to reach, and that metric was not something that we could directly incorporate into our objective, so we did what was called tuning. And that used reinforcement learning or reinforcement learning-like approaches. We even use the pairwise preference ranking approaches that are common in, say, DPO today. So in this work, we wanted to see if the basic techniques that improved machine translation back in the day could also be used to improve alignment in the style transfer approach now. Specifically, we're going to look at running multiple iterations, a fairly standard approach that is underused, and being choosy about the pairs that we optimize on in what's called hope and fear sampling. So let's get into it. The first thing we need to do is create a pseudo-parallel corpus. We start off with our corpus D, which is a style corpus. Every text is labeled with its style, like the orange style or the blue style. And we can use something like ChatGPT or any other large model to create a generic paraphrase, the gray ones. That gray text paired with the original input constitutes a generic to stylized corpus, which we can use to build a generic to stylized model. Then we can combine our original D with our generic to stylized models and create a style to style corpus, where we go from an element in D to generic, then stylize it and put those two things together. From that, we can build a FREF, our basic supervised fine-tuned model that will go from style to style. Now let's get into the preference optimization. For every input, we're going to generate, using FREF, two outputs, one we prefer and one we don't like as much. The denser colors are the ones that we prefer. Using that kind of data, we can run algorithms like DPO or CPO to optimize our model so that it is better aligned and more likely to produce preferred outputs. That's your standard preference optimization approach. We're going to extend that a little bit. First, by not just generating two outputs and scoring one as better and the other as worse, but rather we're going to generate many outputs and then choose hopeful outputs, which is to say ones with a high model score and a high reward score. We would like those outputs. And fearful outputs, one with a high model score and a low reward score. We very much don't want those outputs. We pair the hopeful and the fearful instead of just using two examples. This comes from David Chang's 2012 JMLR paper. The other innovation, so to speak, is that we're going to run our optimization algorithm multiple times. After one pass of DPO or CPO, we change our FREF to be that optimized model and then generate more data and repeat the process over and over again. So, speaking of rewards, we have multiple objectives that we would like to reach in this work. The first is textual style similarity. In other words, how close are we to the target style we are trying to reach? Meaning similarity. How similar in meaning is our style transferred output to the input? And fluency. In general, how fluent and readable is the output? So we have three rewards, and here's an example of an input. True friends wouldn't leave you out there like that, and three different outputs, and nominal scores for each of these. Our standard approach to finding one single objective with which to choose a hope and fear output are to multiply them together, giving us an R, TSS times MS times F. So that's fairly straightforward. The problem is that although the first sentence is our hope output and our third sentence is a fear output, if you look at the specific sub-objectives, it's not always the case that the hope output is stronger than the fear output in all dimensions. In fact, this is an issue that we have some upside down objectives where the hope is actually worse than the fear. And if we have that too many times, we're going to harm performance on that objective. So we're going to use a dynamic reward aggregation when we choose our hope and fear pairs. What that means is we're going to choose an exponent, an integer exponent, for each of our sub-rewards, our sub-objectives, and we're going to choose those so that we minimize the number of upside-down hope and fear pairs before we do the optimization. If we have to break ties, we're going to make sure that we have fewer inverted items for style similarity, before meaning similarity, before fluency. Okay, so now that we've outlined what we do, let's get into our experiments. Our specific metrics and rewards that I outlined in general before. For textual style similarity, we build a classifier based on examples of each style using train Roberta Large. For meaning similarity, we're using an SBIRT cosine similarity with all MPNet base v2. For fluency, again, we're using Roberta Large, and we're building a classifier on the corpus of linguistic acceptability. And all of the models in the system are going to be starting from Llama 2 7b. As far as the actual experiments we're going to run, we have two different corpora of stylistic outputs. We have the corpus of diverse styles, where we have Shakespeare, Romantic poetry, English tweets, a total of 11 different examples. This was used in a previous style transfer paper. And we have Grammarly's Yahoo Answers formality corpus, which has formal and informal. And we're going to evaluate in two ways. One is what we call in-domain. What that just means is that we're going to choose an item from, say, one of the CDS styles and transfer it to another one, and then choose one from the GYFC and transfer it to another one there. And then we're also going to do a cross-domain case where we choose the inputs from, say, CDS, say like a tweet, but then do the transfer in the style of the other data set. So we go into formal, or we go from informal to Shakespeare. So now let's talk about the models that we're going to compare. Of course, we're going to compare STAMP. That's the model I just outlined. We're also going to try some ablations that relate to other published work. We can try just doing the supervised fine-tuning and not the preference optimization, which is basically the STRAP model from Krishna et al. 2020, where we got our inspiration. We can also do preference optimization, but not try the hope and fear iterations. That's Astropop, our previous work from 2024. We can use a different approach to optimization. That's STEER, which uses Quark instead of CPO or DPO. That's from Hallinan et al. 2023. And we can do the basic approach of just using an LLM prompt. We tried GPT 3.5 Turbo 0 and 5-shot examples. So how do we do? Well, if we look at the aggregation, which is to say the textual style similarity times meaning times fluency, we can see that STAMP is stronger than the other approaches. It's a little better than STEER. And it is also better in textual style similarity and meaning similarity, not quite so much in fluency. But fluency is not necessarily that important because the target style may not be fluent. We can see this holds up for out-of-domain style transfer as well. More results are in the paper. And in particular, we did an ablation study to see the effect of iteration and the effect of dynamic aggregation. We can see that dynamic aggregation does lower slightly the aggregated result, but the benefit is that the meaning similarity, that green line, is not harmed. And we can see that iterative approaches really help. In this qualitative example, you can see that some of the baselines are quite bad or possibly not even capturing the same meaning. STAMP at iteration 1 is not particularly good either. The meaning is reversed. But by iteration 9, it doesn't hallucinate, it keeps the right meaning, and it has a strong style. Thanks for sticking around to the end of our presentation. We introduced STAMP and showed some improvements from the old-time machine translation preference optimization literature that are still resonant today and can improve style transfer. We look forward to talking with you at NAACL or elsewhere. Have a good day.